Where does mass actually come from? You probably remember back in 2012, all the excitement around the Higgs boson discovery. It was hailed everywhere as the giver of mass, right? The source of all substance. And it was a huge deal, no doubt, the cornerstone for the standard model of particle physics. But that popular idea, the giver of mass, it's maybe not the full picture for, well, for everything around it.
That's exactly right. It's a profound oversimplification for the stuff that makes up planets, stars, you, me, what we call ordinary matter. The Higgs mechanism, while crucial, is actually responsible for only a tiny, tiny fraction of the mass of that ordinary matter. We're talking about 1%.
Wow, okay, 1%. That's really not much at all. So if the Higgs only accounts for that tiny sliver, where on Earth does the other 99% come from?
Ugh. Oh, well, this is where it gets really fascinating. That overwhelming majority of the mass in protons and neutrons, the cores of atoms, it doesn't come from the mass of the quarks inside them, not directly anyway. It actually comes from the dynamics, the sheer energy of the strong nuclear force.
The strong force. Okay, so our mission today then is to unpack that, how a fundamental force, carried by massless particles, no less, generates almost all the mass of the visible universe. We're going to have to rethink mass, maybe not as just stuff, but as a dynamic thing, like congealed energy.
Precisely. Mass emerging from this, well, this incredibly energetic dance of quarks and gluons inside protons and neutrons. It's all described by quantum chromodynamics, or QCD.
So stick with us. This is going to be a really interesting journey into the substance of reality itself, hopefully giving you a clear path to understanding this puzzle without getting lost in the weeds.
Yeah, and, to grasp this, it helps to see how our idea of mass has changed over time. For a long while, we saw it through Newton's eyes.
Right, the classical view, Fm and all that. Mass was just inherent, an unchanging amount of matter in something. Why was that idea so central back then?
Well, it just was. It was fundamental. Mass was this irreducible quantity of matter. It wasn't really something whose origin you question deeply. It was conserved, like a basic law. But then, of course, 1905, Einstein. Special relativity, and the game totally changed with EMCO.
Yes, the famous one. Everyone knows that means a tiny bit of mass can unleash huge energy, like in nuclear reactions.
True, that's the most famous consequence. But for our discussion today, the really key insight comes from flipping it. MEC second. What that tells us is that any energy contained within a system adds to that system's total mass. Energy is mass, in a sense, when it's confined.
It's still kind of hard to wrap your head around. Mass is energy. Can you give us some real-world examples where that actually happens, even if it's tiny?
Absolutely. Take a simple spring. If you compress it, you store potential energy in it. And because of that stored energy, the compressed spring is actually slightly more massive than the relaxed one.
No way. Really?
Yep. Or heat something up. The atoms jiggle around faster, more kinetic energy. That object's mass increases. If you took the International Standard Kilogram prototype and heated it by just 1 degree Celsius, its mass would increase by about 1.5 picograms. Tiny, but real.
That's incredible. It completely changes how you think about what mass is.
It does. And think about rotation. A spinning baseball has more mass than a stationary one. The Earth itself, just from its daily rotation, has something like over 10 million kilograms more mass than if it were perfectly still.
Wow.
So the big takeaway here is mass isn't some fixed property of a particle alone. It's a measure of the total energy content of a system at rest. That includes kinetic energy inside, potential energy inside, all of it. And that shift in thinking is the absolute key to cracking this proton mass puzzle.
Okay, let's dive into that puzzle then. We need the basics first. The standard model, our best map of fundamental particles, tells us that ordinary matter, you, me, stars, planets, is basically built from just 3 things, right? Up quarks, down quarks, and electrons.
That's the stable stuff, yes. And remember, this ordinary matter, what physicists call baryonic matter, is only about 5% of the universe's total mass energy budget. Most of it is this dark matter and dark energy stuff we still don't fully understand. But that 5%, that's our focus.
Right. And the heart of that 5% are protons and neutrons, the nucleons.
Yeah.
Now, a proton, composition-wise, is 2 up quarks and 1 down quarks.
And the charges work out perfectly. Up quarks are plus 23 charge, down is negative 13. So 2 ups and a down, plus 23, plus 23, plus negative 13 gives you plus 1 for proton's charge.
And a neutron is 1 up, 2 downs. So plus 23, plus negative 13, plus negative 0, neutrons neutral charge. Simple addition works beautifully.
Couldn't be cleaner for charge.
Yeah, but, and here's the puzzle. When you try that same adding up trick for mass, the whole thing just falls apart spectacularly.
Yeah.
The bare masses of these quarks, the mass they get mostly from interacting with the Higgs field, are incredibly small. An up quark is around 2-ish MeV A down quark, maybe 4.5 MeV.
And just to clarify for listeners, MeV2 is just a convenient unit physicists use. It links mass and energy directly, thanks to Einstein. It's standard practice.
Right, so these quarks are barely heavier than an electron, really.
Pretty much, yeah. Very light.
So if you add up the bare masses for a proton's quarks, 2 ups and a down, you get what? Maybe 2 by 2.2 plus 4.8? Something like 9.2 MeV2.
Around that, yes. Less than 10 MeV2.
But the measured mass of a proton isn't 9.2, it's 938.27 MeV2.
100 times bigger.
Exactly. The quarks themselves only account for about 1% of the proton's mass. The other 99%, roughly 929 MeV2, is just missing from that simple sum. That's the proton mass puzzle. It's staring us right in the face. The proton is way, way more than just the sum of its parts in terms of mass. Mass here chose to be emergent.
Emergent is the perfect word. So the obvious question arises, if it's not the quark's own masses, where does all that extra mass come from? And the answer points directly to the strong nuclear force and its theory, quantum chromodynamics, QCD.
The strong force. Okay, what makes it so weird compared to gravity or electromagnetism?
Well, it has some really peculiar features. First, quarks have a property called color charge. It's not actual color, obviously, just a name for a type of charge. Think red, green, blue. And the rule is composite particles like protons and neutrons have to be colorless or white.
Like mixing light red, green, and blue makes white light. So it's a kind of neutrality for this color charge.
Exactly. Then there's color confinement. This is really strange. Unlike other forces that get weaker with distance, the strong force between quarks doesn't. It essentially stays constant. Like, imagine being pulled by a rope with a constant 10-ton force, no matter how far you stretch it.
Wow, okay. Constant force.
Which means if you try to pull two quarks apart, you pour more and more energy into the field between them. Eventually, you put in so much energy that thanks to immanency, it's actually easier for the energy to pop into existence as a new quark and a quark pair, creating new particles.
So you can't isolate a quark, you just make more particles if you try.
You got it. That's why we never, ever observe a free quark. They're permanently confined inside particles like protons and neutrons. It's like a cosmic rubber band you can't snap.
But didn't you say earlier they're also kind of free inside? That sounds contradictory.
It does sound like it. That's the other weird property. Asymptotic freedom. While they're confined overall at very short distances inside the proton, the quarks interact quite weakly. They act almost like free particles zipping around.
So they're trapped together forever, but inside the trap, they're almost ignoring each other. How does that work?
It's these two things together, the long-distance confinement and the short-distance freedom, that create this incredibly energetic environment, like a pressure cooker. All that energy is effectively trapped inside the proton's volume. And according to Einstein, MEC, that trapped energy manifests as mass. It's not just energy stored in the proton. The energy of the force field itself contributes the bulk of the proton's mass.
Okay, so it's the force field's energy, and the strong force is carried by gluons.
Yes, gluons are the force carriers, like photons are for electromagnetism. And crucially, gluons are massless, like photons. But unlike photons, gluons themselves carry the strong force charge, the color charge. This means gluons can interact directly with other gluons.
Ah, photons don't interact with other photons directly, but gluons interact with gluons. What does that lead to?
It leads to this incredibly complex dynamic seething, as physicists say, gluon field inside the proton. It's thick with energy because of all these gluon self-interactions, and it's this energetic field that's primarily responsible for confining the quarks and contributing most of the mass.
So the picture of a proton isn't just 3 little quarks sitting there peacefully. It's chaos.
It's much more like a chaotic soup, yes.
Yeah.
You've got the 3 main valence quarks that define it as a proton, but you've also got a sea of constantly appearing and disappearing virtual quark-antiquark pairs, popping out of the energy field and vanishing again. And swarming through it all is this cloud of interacting gluons, mediating forces between everything. The proton's mass emerges from this whole dynamic mess.
Okay, that's a wild picture. How do scientists actually calculate this? How do they figure out how much mass comes from which part of this soup?
It's incredibly difficult. The equations of QCD are notoriously hard to solve directly because they're so complex and nonlinear, especially with those gluon self-interactions. So physicists use a technique called lattice QCD. They basically put space-time on a grid, a lattice, and then run massive simulations on supercomputers to calculate properties like the proton's mass from the fundamental rules of QCD.
And these simulations, they can actually break down where the mass comes from.
They can, with remarkable precision now. They generally find the proton's mass comes from four main contributions.
All right, let's break it down. What's the first piece?
Okay, first you have what's sometimes called the quark condensate contribution. This is related to how the quarks interact with the background quantum fields, including the Higgs. It accounts for maybe about 9% of the proton's mass. This includes the intrinsic bare mass from the Higgs interaction.
So that's the bit most closely related to the original quark masses, about 9%. Okay, what's next?
Next up is quark kinetic energy. Remember those quarks zipping around inside, confined but moving at nearly the speed of light? All that motion represents energy. This contributes significantly, around 32% of the mass.
32% just from the quarks moving around. Wow. Okay, what's the biggest contributor?
That would be the gluon field energy. This is the energy stored directly in that complex, self-interacting gluon field we talked about. It's the dominant part, roughly 37% of the total mass.
37% from the glue holding it all together.
So,
amazing. And there's one more piece.
yes, the last bit, around 23%, comes from something called the trace anomaly. It's a purely quantum mechanical effect in QCD. Basically, even though QCD seems like it should be scale invariant classically because gluons are massless, the quantum effects actually break that scale invariance, introducing an inherent energy scale into the theory. That energy contributes to the mass.
Okay, so adding those up, 9% from quark condensate Higgs, 32% from quark kinetic energy, 37% from gluon field energy, and 23% from this quantum trace anomaly. That roughly gets us to 100%.
Pretty much, yeah. The exact percentages depend slightly on the calculation details, but that's the basic picture.
The truly profound thing here, then, is that if you look at those numbers, even if the up and down quarks had zero bare mass, if the Higgs didn't give them any mass at all, the proton would still have over 90% of the mass we actually measure.
Absolutely. The overwhelming majority of the mass of the visible matter in our universe isn't fundamental. It's dynamically generated by the energy of the strong force, by QCD.
It really paints a picture of two complementary mechanisms, doesn't it? The Higgs and QCD. Not competing, but working together.
That's a perfect way to put it. The universe uses a two-stage process. The Higgs field gives the fundamental seed masses to the elementary particles, quarks, electrons, muons, TAPIS, the W and Z bosons. It explains, for example, why the W and Z are heavy and the photon is massless. It sets the different initial masses, why the top quark is so heavy and the up-down quarks are so light.
But then QCD takes over for particles like protons and neutrons.
Exactly. QCD dynamics then take those small seed masses and generate the vastly larger mass of the composite particles. It's like the amplification stage.
I like the analogy in the sources. The Higgs provides the tiny seed, but the vast, sturdy plant of the proton's mass grows almost entirely from the rich, energetic soil of the strong force.
That's a great analogy. It captures the scale difference perfectly.
So why do we need both then? If QCD generates most of the mass anyway, why is that little Higgs seed mass still important?
It's absolutely crucial. Both are interdependent. For one thing, the Higgs is responsible for the difference in mass between the up quark and the down quark. The down quark is slightly heavier. That tiny difference makes the neutron slightly heavier than the proton, and that allows a free neutron to decay into a proton, an electron, and a neutrino.
And that decay is important.
Essential. Without it, neutrons would be stable. In the early universe, you wouldn't have ended up with mostly hydrogen protons. You might have had equal numbers, or mostly neutrons, perhaps. The universe would look completely different. Neutron decay is critical for forming the elements needed for stars, planets, and life.
So the Higgs fine-tunes things in a vital way.
Yes. And without the Higgs, quarks would be massless, but protons would still be heavy due to QCD. But without QCD, there'd be no protons or neutrons at all. Just a thin soup of light quarks and leptons, never forming atoms. Technically, physicists talk about QCD causing dynamical chiral symmetry breaking, which generates the bulk of the mass, far more than the explicit breaking caused by the Higgs giving bare masses. But the effect is this emergent mass generation.
So let's connect this back to the big picture. We've explained the proton's mass, and by extension, the neutron's mass. This essentially explains the origin of almost all the mass of, well, everything we see. Stars, planets, us.
Pretty much all the baryonic matter, yes. The substance of the visible universe. Its mass is forged in this QCD furnace.
And that mass energy equivalence idea keeps showing up. Like when protons and neutrons bind together in a nucleus, say helium, the helium nucleus weighs slightly less than the individual protons and neutrons added up.
Exactly, because energy is released when they bind together binding energy. And since energy has mass equivalence, m eats c Teo, releasing energy means the bound system has less total mass. It reinforces that mass is about the total energy of the system.
But let's put this in cosmic perspective again. All this stuff we've been talking about, protons, neutrons, atoms, stars, galaxies, the baryonic matter, it's still only about 5% of the universe, right?
That's the humbling part, yes. According to our best measurements, like from the Planck satellite, about 68% of the universe's mass energy is dark energy, about 27% is dark matter, and only roughly 5% is the ordinary matter whose mass we've just explained.
So this incredibly deep, complex explanation involving QCD and emergent mass, it counts for just under 5% of everything that's out there.
Correct. It's the 5% we're made of, though.
True. So, to wrap up, our understanding of mass has really evolved. It's not just an inherent tag on particles. For the matter we know, it's mostly a dynamic, emergent property arising from the energy of the strong force. The Higgs story is true and important for the seeds, but the dominant story for us, for visible matter, is QCD. The proton's mass is this amazing symphony of confined energy, a real triumph for physics.
It really is.
So here's a final thought to leave you with. We've just seen how the mass of the 5% of the universe we can see is largely an emergent property, generated dynamically. Does this perhaps give us a new lens for looking at the other 95%, the dark matter and dark energy? Could their mysterious properties, maybe even their effective mass or energy density, also be emergent phenomena arising from some deeper unknown dynamics, rather than just fundamental properties of new particles or fields? Something to ponder.